Now we're going to learn a new method. This is a generalization of the spectral method. Remember how the spectral method worked? We took the heat equation and we multiplied both sides by an eigenfunction. We multiplied both sides by sine of n pi over Lx, and then we integrated. And because those eigenfunctions are orthogonal, we were able to get a lot of things to cancel very nicely. So we're going to generalize that. Remember that sine and cosine come from complex exponentials. E to the ix and e to the minus ix span the same space as sine of x and cosine of x, the same vector space of functions, and that's because of Euler's identity. We can write e to the ix and e to the minus ix as two different linear combinations of sine and cosine. And in the same way, you can write sine and cosine in terms of e to the ix and e to the minus ix. That's a very good thing to know how to do, to convert back and forth between complex exponentials and trig functions. Well, so now we're going to convert from trig functions to complex exponentials, and that's because this is going to be a more general method. We're going to look at the problems where the domain is not just 0 to L, a finite domain. We're going to, for the first time now, look at the case of an infinite domain. Consider the entire real number line from minus infinity to infinity. That will be our domain. And so the boundary conditions are not going to be the same kind of Dirichlet boundary conditions where the function is not going to equal something on the boundary because there is no boundary. Instead, we're going to just enforce that the solution goes to 0 as x, or in this case y, I guess, y is our space variable, as y goes to the endpoints of plus and minus infinity. So it's like homogeneous Dirichlet conditions, as close as we can get for the case where we don't actually have a boundary. So sometimes we call this the free space heat equation. So now the transform method, it's called the Fourier transform. Fourier transform is going to be kind of like the Laplace transform was last semester. Do you remember the Laplace transform? Well, Laplace transform said we took a function and we multiplied by e to the minus st, and we integrated over the entire domain, which for ODEs was 0 to infinity. Here is the Fourier transform. The Fourier transform, instead of e to the minus st, it's x instead of t, it's e to the minus I omega x. And so instead of e to the minus sx, it's e to the minus I omega. The I, it's complex instead of just one thing all lumped into s. Sometimes some people like to think of, in the Laplace transform, they like to think of s being a complex number, which you could write as I omega. So here, for the Fourier transform, since this is a generalization of the Fourier series, which is sines and cosines, this then is it. It's e to the minus I omega x. So we take, if we want to do the Fourier transform of u, that means we take u and multiply by that kernel, and we integrate from minus infinity to infinity. That's the entire domain, is now it's minus infinity to infinity. And so the Fourier transform takes a function of x, this is like an x land, and then the output is now not a function of x anymore. X is what we call a dummy variable over here. Now it's a function of omega. And so last semester we used capital letters to denote the Laplace transform side. Like we used capital letters that were functions of s and lowercase letters that were functions of t. So now that we're doing Fourier transforms in space instead of time, we'll still use little letters as functions of lowercase x, but we will put a hat over the Fourier transform of a function. So u hat is the Fourier transform of u. And notice these are now functions of omega. This is like the omega world. So now here's why we like Fourier transforms when it comes to partial differential equations. Remember, in ordinary differential equations, we were able to use the Laplace transform to take an ODE, a differential equation, and instead write it as an algebraic equation. And there's a property that's the same, comes from the same place that we're going to use again. What if we put a derivative or two into the Fourier transform? So we're looking at u double prime going into the Fourier transform. What's the relationship, or what happens when we put a double prime in here? The technique that we use is integrate by parts. And if we do that twice, it's like taking a derivative off of u and putting it onto here, onto the exponential. What do we get when we take the derivative of exponentials? When we take the derivative of exponentials, there's a chain rule. And so out front, we put an I omega times itself. And so if we do that twice, this becomes an I omega squared, minus. The minus sign, the minus I omega is what comes out during the chain rule. So minus I omega squared. And remember also, when we integrate by parts, we put a minus sign, but if we're doing it twice, that minus sign will cancel. So if we put two derivatives on u, then we get minus I omega squared coming out, and then the results, the rest of it is still u hat. So derivatives in the world of x in real space become times omega squared in imaginary space, where omega is kind of like an imaginary space. So now you can see on the beginning of your handout that if we take the heat equation, us minus uyy equals 0, if we do the Fourier transform to both sides, if we put a 0 in for u, the integral of 0 is 0, so the right-hand side stays equal to 0. The Laplace transform of us is u hat s, but since we're doing this with the space variable, the second derivative with respect to y becomes that I omega squared. And of course the minus sign squared is 1. So that's where that first line comes from. And then you can follow on the handout where if I squared is minus 1, you can fix the sign. And so you see we get the ordinary differential equation now, that the derivative of u hat with respect to s plus omega squared u hat itself equals 0. And so the heat equation becomes this. This is that same first order linear differential equation that we've had this entire handout. So it's interesting how whatever method we use for the heat equation, all these different methods amount to taking care of the space variable. Here the Fourier transform integrates, and x is a dummy variable, and we get this that's a function of s. And so check all of the methods. What we always found was that we'd end up with ODEs, and with respect to time, we always ended up with the first order linear ODE.